So there are certain rules that we are enforcing because that's what makes it fun. So you heard D-Wave is giving you 1 minute. We are giving you 5 minutes. So 5 times more. So seriously, every speaker gets 5 minutes sharp. And there's a timer which will hopefully help you. There will be some sort of noise at the end. So please try to stay within 5 minutes. If you want, then we will basically stop you. You can use it however you want. You can use 3 minutes to plug in your computer and 2 minutes to talk. You can use 4 minutes to introduce yourself, or have 1 slide or 50 slides, or leave time for questions or not. So it's your 5 minutes. Please come here earlier so that you can get mic'd, or you can use this mic or podium mic, so that we can kind of streamline this. And there is time, plenty of time after those talks actually to interact. So there's like 35-minute break, and then some of you have posters. So please kind of make yourself available for others if they have questions. What else should I mention? Posters. Yeah, so I think I mentioned everything, and so hopefully the speakers know what the order is. If not, raise your hand and I can, but it's on the web, it's on the agenda. So Stephen is first because he knows the rules, he's done it before. So Stephen, come over and we will start the timer. Do you want this one?
This mic on? Yeah. Okay. So this talk is, someone commented at lunch, less technical than I usually deliver at these lightning talks. But I decided on this topic because I think as practitioners and purveyors of large data systems, it's a topic that we need to be involved in and worry about. So I'm going to talk about how to, it says eliminate, but really I mean reduce, because you're not going to eliminate, but reduce bias when we deploy machine learning. That's the main point here. So, there's this perception that because we're doing, the mathematical stuff behind the scenes, and it's math and it's not humans, that we're eliminating bias. And hopefully in this room we understand that that's baloney. Right? There is bias, right? But people's perception is because it's math, because it's machine learning, we've eliminated the bias, right? And it's interesting that when you do surveys out there in the world, there are some people that are very afraid of machine learning and AI and deep learning, and then there's some people that are very not afraid of it, and are very encouraged by it. And the ones that are most excited by machine learning and deep learning and being involved in decision making are the ones that lived in corrupt societies. Because the ones that live in corrupt societies, they believe that if you get the humans out of the decision making process and you let the algorithms do it, then we're going to get rid of biased decisions. And it's not really true, right? This is fiction. And what we have to understand is that there are lots of places where bias can be introduced into AI solutions. There's a mathematician, Cathy O'Neill, who wrote a book called Weapons of Math Destruction. Right? And I think she makes a very interesting observation. She's a Berkeley, Harvard-trained mathematician. And her proposition is, in fact, algorithms are really opinions embedded in code. And because the opinions are embedded in code, they're opaque and they're hard to challenge, right? And yet there is bias in there. There's bias in how you frame the problem. What are you optimizing for? So if I build a recommendation engine using machine learning and deep learning to figure out what song should I recommend to you that you're going to listen to, right? Well, how I frame the problem matters, because maybe I have an objective. Yes, of course, I want you to like the song, but I also want to minimize the royalties that I pay to the person that made the song. And depending on the deal that I have with different artists, I may actually recommend a song that you like a little bit less, but I pay much less royalty on. So I've introduced bias because my objective function might be different than your objective function. How I select the data to include. So I might decide that songs with profanity in them should not be included in the set of things that I'm going to recommend to you. So I've introduced bias because I don't think you should listen to songs with the F word in it, right? So how I select the data, how I define the objectives, how I prepare the data, these all introduce bias. AI algorithms are biased, and this is one of the biggest issues in sort of getting AI accepted by society, right? And yet it's not the math that's biased, it's the humans that's biased. The bias is sourced from humans. The bias is not sourced from the algorithms per se. Okay? So my claim is, not my claim, it's a claim I think well understood by mathematicians, that the algorithms, the mathematics in the algorithms are not inherently biased, but the data that you use in the algorithms to do the training is probably biased. And that's the bigger issue. So if the algorithm is only as good as the data that we use to train it, we need to be much more methodical about how we obtain the data sets, how we prepare the data sets that we use for the training. So the bad news here is that the AI algorithms are as prone to bias as the real thing that we're attempting to emulate, right? AI, artificial intelligence, we're trying to emulate humans. Humans are biased. AI is also biased. But it actually gets the bias from the humans. We can proactively manage this, right? If we're smart about it, we will manage. We need standardized approaches for developing and deploying the AI algorithms, and we need to build in the vetting of the data to be successful. Thank you.
So, hello, my name is Markus Paradies, and I work for the German Aerospace Center. And in the remaining 5 minutes, I'm going to talk about near data processing in deep and cold storage hierarchies. So today, if we look at the storage hierarchy and its current coverage in the database research, then we will likely see a trend in terms of coverage in papers leaning more towards the faster layers of the storage hierarchy, mainly ignoring basically nearline, offline storage that is tape-based. Even worse, we see upcoming storage technologies that already receive quite a lot of research attention, mainly leaving everything that is tape-based or nearline storage not really interesting. So now you might ask yourself, well, nearline storage, tape-based system, isn't that kind of all old stuff that we don't really care anymore about? And in fact, I want to convince you with this picture that at the German Aerospace Center and also at other facilities, there are active data archives that, due to data volume reasons and due to cost reasons, mainly still rely on tape-based systems. And they are usually fully automated, so you can see here a robot that usually then picks up here the tapes, brings them to the drives, then the drives wind up the tape, and then you can read. If you now look at scientific application domains, for example, Earth observation, radio astronomy, weather forecasting, then in terms of data volume, they are all about in the same ballpark. So usually it's a couple of dozens of petabytes that they store. And usually these kinds of architectures are accelerated by a disk cache in order to speed up data retrieval, which is often about 10% of the size of the overall data. So what is now the problem? The problem is data movement. We've heard it today in the first talk. Data movement is really a pain point. And active data archives and also their catalogs can be seen a little bit like an Amazon, but just for data. So we want to access data, we want to retrieve data. So it's a little bit like Amazon Prime, but in reality, it's not really Prime, because it takes usually longer to retrieve data from some archive than to order a book on Amazon. And even worse, usually we don't have really SLAs and access latency. Access latency is going to be between minutes and hours, and tail latency can be also up to multiple days. And even more for scientific domains, historic data analysis is becoming more and more important, and these data requests can easily retrieve a couple of hundreds of terabytes. If we look at the architecture, then we can see that there is a clear disaggregation between storage, where the data resides, and our fancy compute facilities where we have all the hardware accelerators that we've heard about today. So the problem is we have to get the data from these archives through several disk cache layers to the compute facilities, where we have massive compute power, but the problem is really data movement. So what we kind of propose here is to select certain operations that usually reduce data volume and put them on the data path and basically enable processing in the network and in the storage by either using FPGAs, for example, and also for SSDs. There's now a term called open channel SSDs that also allow to open up these storage devices in order to make them programmable. So we started a research project called CryoDrill, which aimed at enabling near data processing, in particular for cold storage. So our focus here is really on archival disks and tape-based systems. And instead of just taking a single near data processing opportunity, we want to look at the entire data path. Yeah, and this basically enables us to leverage all the compute power that sits in the network, in the storage devices, and then finally also, of course, in the compute facilities. And so we started now talking to research scientists in order to initially just identify the operations that are actually worth pushing down the storage hierarchy closer to where the data resides. And then finally, just a personal remark. So I have a strong in-memory database background. So for me, it was also a bit of a change to start now looking into tape-based systems. But after I got a little bit more into it, I found it actually a quite interesting research topic, primarily because it can have a very high impact on scientific domains, but it's still kind of overlooked by the community. And it's just fun to work on. Thank you.
Hello? Hi, let me see. Hi, I'm Edward, a PhD student at Stanford University, and today I'll be talking about some of the research I've been doing on data summaries for large-scale aggregation. So if you want to support interactive query processing on large data streams, including like event logs or server logs, let's say terabytes per day, one way to support much faster latencies over the much larger data set is to construct summaries of your data and then operate over summaries rather than the actual raw data stream. And so what a system like Druid will do, which is an in-memory OLAP store, is partition the data into 15-minute segments or arbitrary segments of some length, and then store one summary for the data for that segment of time in a single block. Then what you can do is, if you summarize the data for some 15-minute interval, which can include counts or sums or sketches, such as hyperlog sketches, then if you have a query over a longer time range, let's say a half-hour block, you can serve the query by just looking up the relevant summaries without having to actually go back and do more expensive raw disk scans. Your query is now approximate, of course, but the trade-off is that you can answer it much faster because you can keep all these summaries in local memory. The challenge here, though, is once you start operating over multiple summaries to answer a single query, you get error accumulation. So if, for instance, you're trying to understand frequent IP addresses over some long time range, like the past day, and you're trying to answer this using a data system that has stored summaries for 15-minute blocks, what you have to do is, if each block stores an approximate sequence of counts for the top IP addresses or something similar, and it will introduce some error epsilon in answering a query for counts within that single block. And if now you're assembling a couple dozen blocks to answer queries over a longer range of 7 hours, the total worst case error you'll get from aggregating these blocks scales linearly with the number of things you have to aggregate. This is bad, and it gets even worse if you have to aggregate along other dimensions besides time, such as location as well. But there's a lot of hope for improving the quality of the error degradation in these situations when you have multiple summaries. And the observation we have here is that if you're trying to estimate frequent item counts, they're going to be either overestimates or underestimates. So in the worst case, as I described earlier, if you're using a sketch such as like a count-min sketch or a Misra-Gries sketch for frequent items, it's going to have a consistent bias. It's going to consistently either overestimate or underestimate counts for different time windows. And then you get sort of this linear error buildup over longer ranges. If you are maybe a bit more savvy and you store like an independent sample, you'll get unbiased errors for every time window, and you can expect modest error cancellation due to like the random oscillations for overestimates and underestimates. And our goal in our research has been to sort of think about, okay, can you do even better? Can you set up the sketches in a way so that if you expect to merge a certain sequence of summaries, then you can get perfect cancellation, meaning that the final error you get is no worse than the error from a single summary for a single, more fine-grained time block. And we believe there's a lot of hope to achieve improvements in this domain. So if you're trying to just study a single sequence of frequent item counts over a contiguous time range where you're combining data from k different summaries, and you use a more standard summary, such as a count-min sketch, which has a consistent bias, the error grows linearly. Or if you use maybe another naive approach of just storing the most frequent items for every time window, you will consistently underestimate any item that you did not store for that time window. If you do sampling, you can see how this square root level growth from random cancellation gives you a big improvement when you're aggregating 100 different summaries. And we've been developing methods that can achieve much better, theoretically, maybe logarithmic growth, in practice, almost constant growth in the error as you combine more and more sketches. And the intuition is if you know you'll be combining sketches in a contiguous time range, you can sort of design the sketches to compensate for previous errors that other sketches or summaries have made within that time longer window. So to summarize, if you are operating over data at a scale where you have many, many different summaries partitioned along time or location or other dimensions, and you're now actually answering queries by combining different summaries, so it's like a two-layer system, then the approximation error is something to be aware of. It could grow as you combine more and more summaries. You have this like compounding error. But there's a lot of potential to design summaries for better error cancellation than you would get if you just use off-the-shelf data summaries. And these depend on your aggregation patterns, and they also depend on what kind of queries you want to make. There's a lot of space for different kinds of algorithms for different combinations of these features. And I'd love to hear any feedback. If you're using data summaries to manage data volumes or you're aggregating them in unique ways, please come stop by my poster or send me an email. Thank you.
Good afternoon. My name is Dennis Weng. My colleague Wensheng is sitting over there. We both are from JD.com, one of the biggest e-commerce company in the world. Data analytics is a key enabler to our effective business decisions. Our platform is based on heavily customized Apache Hadoop systems. So it constantly manages the computing and the storage needs for the data warehouse, ETL, and the data analytics and machine intelligence with 50K servers. More than 1 million jobs queries are running every day. So the total data set occupies towards exabyte storage, about 800 terabyte. So most of the recurring batch jobs are running very mature and stable MapReduce technologies such as Hives. So we are working on evolving the computing technologies to be more cloud native and container friendly, and leverage the in-memory computing to deliver high performance efficiently and support batch streaming and machine learning data analytics jobs under a consistent framework. So the Apache Spark stands out to be a good fit candidate. So this is a logical query plan for typical procedures with a very complicated DAG dependencies. So Spark is able to reduce the query completion time by about 70%. So at the current stage, Spark has grown to be a mature and reliable computing engine for us to migrate the Hive queries. So however, in practice, it turned out to be the involving the computing technology to Spark is very challenging and problematic. So besides all the awesome work done by the community, through the process we need to consider and address the compatibilities. So running stability and the performance running issues, our ultimate goal is to give a job completion time, deadline, and run it with most cost-effective configurations and during the transition time. The Spark and Hive jobs have to run peacefully in the same young cluster, later the Kubernetes. So compatibility with Hive turns out to be the biggest challenge, as I said, and the manpower consuming problem. So there's a lot of dedicated incompatible issues raised up during the process, most due to the years accumulation of queries following the query language of early version of Hive. The most notable problem is about the Hive user-defined functions. So for example, there's no reliable way to know where a legacy Hive UDF is thread safe or not. So that creates a much headache for us. And when we run with a Spark task execution model, it's inherently multi-threaded. So all of these compatibility issues come out, and so we have to solve in the production system. So stability. So most of the batch queries are part of a critical production pipelines that are scheduled to run at the early morning and need to complete under an explicit defined SLA. So additionally, at the promotion days, of this the incoming data has to be increased by one of order of magnitude. The computing engine needs to complete the queries reliably despite the significant data volume changes. So performance, the other source of issue is the executor of the memory, auto memory problems that is difficult to eliminate at the tail cases. So we integrate the various JVM profiling technology and jointly turn Spark memory configuration and the GC collection, garbage collection to reduce the all problems. So lessons we learned, the large-scale production job migration is a significant effort, and the data consistency is critical, and the process tools are very important. So next thing we do, we complete the migration effort, deploy the cost-based optimizer, and the JVM optimizations, and I think that's all then. Thank you very much.
Okay, you guys can hear me? Okay. So I'm Alon Peled, I'm a social scientist from the Hebrew University of Jerusalem, and I'm going to talk to you today about open data. Open data is basically data that is released by governments, municipal level, all the way to the EU level. It's today one of the largest type of data on the web. It's supposed to be only CSV and Excel, but it's everywhere. It's free. You can download. You can mix it with your business and do stuff with it. It appears usually on open data portals. There are special portals that appear in any language everywhere. The potential of open data is huge, and it's been known for a while. It started in 2009, and one study, for example, said that it could add trillions of dollars to world economy if it's done right. There's three problems with it. First, it's very difficult to discover useful open data for your business. Second is the classification is very poor. The public officials, municipal level to the EU level, are never given enough time, resources to do the job. And furthermore, and that's probably the most critical problem, they do not know how to do a better job tagging their data. Someone deals all their life with waste management. You can't expect from him or her if they upload their data to the web, to have tags or keywords that are not about trash. All the keywords will be about trash. That's all they know. They've been doing it for 20 years, and thank God they're doing it for 20 years like this. And finally, it's very difficult to use it. This is an example of what my research is trying to accomplish. Basically, you would like to get, as a result of any query, this is an example of, I don't know, say you want to build, to add some open data, useful open data to your business, selling some stuff to natural gas pipes. So basically, you'd like to get in each row a project name and how many billions of dollars and what year and so on and so forth. The problem is it comes from different data sets all around the world, and it's buried deep inside the data, and data could be very large. This is an example of how a result, if you want to buy a Toyota car, this is how the results about Toyota flows would come in Google. And this is how you would like to get it, and what I'm trying to do in my system. Basically, you would know each row would represent something in each data set in different languages from different places. And so, and another example of basically you're looking for a job and you're looking to find a job through a public tender. This on the left side is how the Google result would look like. On the right side, how I'm hoping my system will output the result. So each row is an opportunity for your business. The system I built basically crawls and specializes in open data as an item, different than, let's say, an HTML page. And what it basically does, the heart of the system, after it crawls and basically does the initial indexing of whatever metadata is out there, is basically this thing called MECA, metadata extraction and classification algorithm. I rely on the assumption that public officials will do a bad job tagging their data. I treat the initial metadata they upload as nothing but hints. Hints for what the data might be about. And the entire purpose of my project is basically to enrich the metadata. And so this is how MECA happens, basically. Since I'm a social scientist, if I invent anything useful in computer science, probably I'm doing something wrong. I do not know how to do it, and I do not intend to do it. My purpose is basically using stuff that computer scientists have already developed and lost interest in, and mix it in interesting ways in order to provide actual real value, to basically better classify the open data of the world. So that's the heart of it. A couple of patents came out of it. Virtually all the solutions that you will see on the marketplace today to how to do it, they do a bad job, and the reason is, again, they rely on whatever metadata was initially provided by the vendor, by whoever uploaded the data, and they do not know how to tag the data well. There's today already, about 4 months ago, Google came up with a new engine that basically you can search for data sets, open data sets. The problem, again, Google itself relies on the initial metadata that whoever uploaded the data. There's something that came from a company, another search engine for data sets, open data that came out from a company that was established based on the research I did in my lab. An example would be of the best classifiers, let's say the NOAA, the famous NOAA agency in the United States. Even the best people, like at NOAA, when they upload a data set, you'll never get better than NOAA. You'll never know that this thing is actually useful for agriculture or might be useful for waste. You'll have to discover it. You'll have to work really hard unless you use a system like the kind of system I'm trying to develop in my lab. So here's an example of basically how you do. I basically attack I take one item, one indexed item, and I attack it with multiple techniques that we can talk about later on when you come to my poster. And my goal is basically to make these known systems work really hard and discover that this data set is also about waste management, or in this case, about agriculture. And if you come to my poster, I'll also tell you about how I discovered the politics of databases and how you can track your trash traveling around the globe. Thank you very much.